So we're going to start a new chapter today called Nuclear Chemistry, and that's going to focus on the nucleus, obviously. So we're going to go into the center of the atom now. All the reactions we've done so far up until this point have dealt with electrons. So we talked about electrons being shared or being transferred, and we focused on moving around the outside electrons. But now we're going to move into the center of the atom, and we're going to focus on the nucleus. So nuclear reactions occur when a nucleus either gains or loses protons and neutrons. So again, the two particles that are in the nucleus are protons and neutrons, so if you trade those around, it's going to be a nuclear reaction. And just like the other reactions, the whole purpose of this is to make the atom become stable. So if a nucleus is too big, meaning that it has too many protons, since protons are all positive, they repel each other. So if you have too many positive charges all in one place, they're going to break apart and split up, and that's what we call nuclear radiation, is when those nuclei are splitting out particles. And all elements that have 84 protons or more in the nucleus are automatically going to be radioactive. So again, the major idea here is that nuclear reactions happen to make the atoms more stable. The next word is transmutation, and you can probably see the smaller word in that is mutate, which means to change. So if you're changing around the number of protons, since the protons identify which element it is, if you change the protons, you're going to get a completely new element. And that process is called transmutation, when you change the element by changing the protons. And just like on our other reactions, the law of conservation of mass has to be conserved. So basically you have to have the total mass of the products has to equal the total mass of the reactants. And same thing with atomic numbers. You can't create or destroy protons, so if you start with a certain number of protons, you have to end with a certain number of protons. And if you look at this symbol, I know it's been a while since we did this, this is way back to the very first chapter. The top number on that symbol is the mass number, which tells you the protons and the neutrons. The bottom number is the atomic number, and that's the one that tells you the protons. So for these reactions, we're going to be using those numbers to make sure that they're the same on both sides. And there's 3 different particles that we're going to talk about. There's not much that you need to memorize for this chapter, but you do need to make sure that you know these particles. And the first one is called an alpha particle. You need to know that an alpha particle is a helium nucleus with a 4 and a 2. The 4 is the mass and the 2 is the atomic number. So alpha decay happens when the nucleus spits out an alpha particle. And if you look at that picture, you can see that it has the black parts of it are the neutrons and the pluses are the protons. So if you have a really big nucleus, one way it can become stable is to get rid of some of those protons by spitting out an alpha particle. And notice that the alpha particle has 2 protons and 2 neutrons. So again, what you need to memorize is that it's helium-4 2. It has a positive 2 charge. And compared to the other particles we're going to talk about, this one is the biggest, which means that it's the lowest energy. It's so big that it can't really move that fast. And it's so low energy that it can be stopped by a sheet of paper or by your skin. So if somebody was shooting you with alpha particles, it wouldn't hurt you at all because they would just bounce off of your skin. During this process, since you're spitting out 2 protons, you're going to get a new element. So anytime you have alpha decay, transmutation will occur. And again, transmutation is just getting a new element by changing the number of protons. So let's walk through how to do this, and I'm sorry I can't write on the screen here, so you may have to come see me in class if you're not sure how to do this. But for the first example, you've got uranium-238 and 92. And if you don't have a periodic table out, you want to go ahead and pause the video for a minute and go ahead and take out a periodic table. So what you're going to do is spit out an alpha particle. So on the other side of this arrow, you want to write He for helium with a top 4 and a bottom 2. Helium-4 2. And then put your plus sign. And the idea is that all the numbers on the left of the arrow have to add up to the same as what's on the right of the arrow. So if you have 238 for uranium at the top, all of your top numbers on the right of the arrow have to add up to 238. So since you already have 4 from the helium particle, you're left with 234. So in addition to the alpha particle, you're going to have another particle that has 234 on the top. On the bottom for uranium, you have 92. So everything on the right of that arrow needs to add up to 92. And you already have 2 protons in the alpha particle, so your other number on the new element is going to be 90. So basically you have 234 over 90. And then remember, it's the atomic number that identifies what the element is. So you're going to find 90 on the periodic table, and that is TH. So you have turned uranium into an alpha particle, and TH that has a 234 on the top and a 90 on the bottom. And I want you to try some of those, and then if you missed class today, just make sure you come see me and show me that you understand how to do these equations. They're not hard at all, but I might need to show you how to write them out. Let's move on to the next particle. The next one is beta, which is essentially an electron that's inside the nucleus. And for beta, you can either write a lowercase e, or the beta symbol is a capital B with a little tail sticking down. Those are the same thing. And you have a 0 on the top, a -1 on the bottom, and you do need to memorize that. Because an electron or a beta particle has no mass, it's going to be much higher energy. So it's higher energy than the alpha particle was. So it can go through your skin, but you could stop it if you had something thicker like foil or a piece of wood. And this is also going to create a new element, so we call that transmutation. These particles are going to be the same idea as the alpha, except you're just going to have 0 and -1. So if we do it for uranium, if I say that it undergoes beta decay, you're going to put the e, lowercase e over here, with a 0 on the top and a -1 on the bottom. Then put your plus sign, and for our new element, we just have to make sure all the numbers add up to these numbers. So since we have 0 on the top for beta, for the new element we're going to have 238, because it has to match what's over here. And be careful with that -1. If you have a -1 on the bottom, it's tempting to say 91, but 91 plus -1 does not give you 92. So on the bottom over here, you're going to need a 93, because 93 plus -1 gives you 92. So your two new numbers over here, you have 238 on the top and 90 on the bottom. I'm sorry, 93 on the bottom. And if you look up 93 on the periodic table, it is NP, Neptunium. Try the next two and show me in class just to make sure you got those. And our next particle is called a gamma, but it's actually not a particle, it's more like a high energy wave. And since it's not a particle, it's more like a wave, it's much more dangerous. So this one travels the fastest, and it can go through the most things. You can block it if you have something thick enough, like several centimeters of lead, which is really dense, or if you have several meters of concrete. This one almost always occurs in addition to alpha or beta. So if I say that it's alpha and gamma, you would go through the alpha process and then just stick a little gamma sign, which looks like this up here. And I can show you how to do that in class too, just remind me. Since the gamma doesn't have any numbers on it, it's not going to change the mass number or the atomic number, so in this case transmutation does not occur. So this is the chart that you need to memorize. This is the one of the few things you'll need to memorize for this chapter. So go ahead and pause the video and take a minute and copy down this chart. This is just a picture that shows you how they can travel. So notice how big the alpha is compared to the beta. So it's so big that it gets blocked by paper or skin. Beta is tiny, so it can go through the paper, but it can be blocked by wood. And then gamma is that high energy wave that's so high energy it can go through almost everything. You can block it, but it's got to be something really thick, like lead or cement. And our last two things for today are nuclear fission and nuclear fusion. So fission is when you split in half or split apart a nucleus that's really big. So the key word there is splitting. What usually happens is if you take something like a neutron and shoot it into a uranium nucleus, the uranium nucleus will split into two smaller nuclei, but you also get 3 additional neutrons. Those neutrons then go to hit other uranium atoms, and all of a sudden you've got what we call a chain reaction because it just continues on and on. Every time one uranium is split up, you get more neutrons to hit other uranium atoms. So this is called a chain reaction, which is a continuous series of fission reactions. In the process, a ton of energy is released. We can use that energy for several different applications. So one way we can use it is for the atomic bomb, which you've probably seen pictures of the mushroom cloud. This is when you let that chain reaction go uncontrolled. If you just let it go crazy, it's going to create a bomb that looks like a mushroom cloud. But we can also use it for good if we use it for nuclear power plants. So if you look at this picture, the neutron slams into the uranium, which breaks into 2 smaller atoms, but you also get 3 neutrons. And those neutrons then hit other uranium atoms. But if we control it and slow it down just a little bit, we can use that energy for electricity. So nuclear power plants use fission reactions, but we control them. And the last thing is nuclear fusion. So this is when you have 2 or more smaller nuclei that are going to stick together to form a big nucleus. So this is the opposite of fission. Fission, you break it apart. Fusion, you're putting it together. So if you look at this picture, deuterium is just an isotope of hydrogen, and tritium is as well. So if you take these 2 hydrogens and you stick them together to make helium, in the process you get a whole lot of energy. And it's good energy because it's clean energy, but the problem is we haven't been able to do this on Earth yet. So it occurs on the sun. Anytime you feel the sun's energy, if you feel heat from the sun, what you're feeling is energy from this fusion reaction that's happening on the sun. But the reason that we can't actually do a fusion reactor, like to get electricity, is because of the high temperatures that it takes to get it started. So 360 million degrees Fahrenheit is what you would need to start the fusion, and it's just difficult to have that high of a temperature. They had this in Spider-Man 2, I think, if you're familiar with Spider-Man 2. So the last thing is just how I remember the difference between these 2 words, because they're kind of confusing because they sound so similar. Fission has an I, like the word split, so just remember fission is splitting. Fusion has a U, like the word put, so it's putting together. And that is all for today. If you missed class today, just see me and make sure you get the worksheet so you can practice some of those reactions, and make sure you check with me to see if you're doing those reactions correctly. And that's all.